This is the screencast for section 7.2, example 5. We're going to integrate with respect to y this time. Now remember, in the previous examples that we did, your rectangles are vertical. You are taking the height of your rectangles under the top curve and subtracting out the rectangles underneath the bottom curve, getting rectangles that stretch from each curve, and those rectangles have a teeny tiny little width that we call dx. Well, now what if we come across curves that are more of a vertical type curve? Now I know what you're saying, these don't pass the vertical line test, but that's okay. Sometimes they don't. We don't always have to deal with functions. But if we have these curves that are a little bit more vertical, if you try putting in vertical rectangles in there, that's going to be really complicated. I don't know, what do you get, a patchwork in some rectangles? That just, it's kind of getting messy. So instead, we're going to make our rectangles horizontal. So their height is going to be the right curve minus the left curve this time, and then their thickness is going to be dy, a little teeny change in y on the y-axis. So their thickness is dy. So your basic strategy, much like the integrating with respect to x problems, is now you're going to solve each equation for x in terms of y, so it's the antiderivative from f of y minus g of y. You're going to have your lower limit of integration, the lower y value, and the upper limit, the upper y value. And you're going to take the right function minus the left function. So this whole big area underneath the right function, and then you're going to subtract out the area underneath the left function to leave you with the area in between. Now example 5, it tells you you're integrating with respect to y, but let's see why that is. Find the area of the region R in the first quadrant. Okay, basically this is the same as the last page, or the same as the last example, so I wrote that down here. Now instead of making vertical rectangles here and having the lower boundary change, I can make horizontal rectangles in this case, stretching from x minus 2 to square root of x. And then the thickness of each of these rectangles is going to be a little change on the y-axis, or dy. But be careful, you can't use x minus 2 and square root of x, because we're integrating with respect to y. So if you're having a dy at the end, the only variable that can be in your integrand is y. So the first thing I'm going to do is take each of these equations and exchange them, or solve them for x in terms of y. So y equals x minus 2, just going to add 2 to both sides, and I get that x equals y plus 2, so that's your new boundary on the right. Then the other one, y equals square root of x, that's your left boundary. Square both sides, and I get y squared equals x. So now I can integrate from my lowest y value, 0, to my upper y value, 2. So I want my rectangles to stretch from 0 to 2 on the y-axis. They are going to stretch out as far as y plus 2 minus y squared. That's the left boundary that we're going to subtract away, the area between it and the y-axis. And now I can just integrate with respect to y. Fundamental theorem part 2, simplify, and I get an area of 10/3. And again, if this was a big 2 by 4 rectangle, this area would then be 3 1/3. So out of the 8 square units of area, we have 3 1/3, a little less than half, and that seems about right. Then now try problem number 11. Says find the area enclosed by the graphs of the two curves by integrating with respect to y. So they give you that you're integrating with respect to y. We're going to ignore that for a second and just pretend like we don't know. So first of all, in number 11, these equations are neither solved for x nor y. How annoying. So I need to solve them for y to put them in my calculator. So the first one, I get y equals plus or minus the square root of x plus 1. So in y1, I'll put the plus version, and y2, I'll put the minus version. The second equation, same thing, take the square root of both sides, I get the plus or minus. So in y3, I'll put the plus version, and y4, I'll put the minus version. And then my graphs look something like this. Of course, we need to find those intersections, so I did that. But now, as you can see, it's going to be difficult to make your rectangles vertical because the same curve is going to be used for the top and bottom. Now I get it. Technically, the top is positive square root x plus 1 and the bottom is negative square root x plus 1. And then you can change the boundaries over on this side for positive square root 3 minus x and negative square root 3 minus x. That's fine. That's acceptable. But that's a lot of work. I think it's easier in this case just to do one right boundary and one left boundary and do horizontal rectangles. Make this a dy problem. So now I'm going to solve each equation for x so I can make this a dy problem. So that first one turns into 3 minus y squared. The second one is y squared minus 1. So I'm going to integrate, because it's a dy problem, the right curve 3 minus y squared minus the left curve, y squared minus 1. And then my boundaries, my lower bound is going to be the lower y value of the intersection, so that's over here, that's negative square root 2 and positive square root 2 respectively. So I'll put those in, negative square root 2 to positive square root 2. And then I get that the area after I integrate with my calculator is 7.542 square units. Again, I could have drawn vertical rectangles, but then change the boundaries over to the right side here. But I decided that was going to be hard because then I'd have this top minus this bottom, and then I have to add this top minus this bottom. So instead, I'm just going to make some horizontal rectangles and just use the right minus left strategy so that I only have one integral to take care of.